Imagine the universe as a baby, a tiny, fragile entity, full of potential and mystery, waiting to grow and evolve. This baby, however, is not just any ordinary baby, it's a cosmic infant, born from the most extraordinary event in the history of everything. Now imagine trying to see that baby, but it's billions of years in the past. It's like trying to peer through a foggy window into a time so distant, it's almost beyond comprehension. Yet, this is exactly what scientists have managed to do. It sounds impossible, right? Well, thanks to something called the cosmic microwave background, or CMB for short, we can catch a glimpse of the universe as it was just a short time after its birth. This faint glow, this ancient light is like a photograph taken when the universe was just a baby. This faint afterglow is like a baby picture of the cosmos, telling us a story about how everything began. It's a snapshot of the universe in its infancy, a time when it was filled with hot, dense energy, and just beginning to cool and expand. The universe started with an unimaginable explosion called the Big Bang. This wasn't just any explosion, it was the birth of space and time itself. In an instant, everything that would ever exist was created from a single, infinitely small point. This wasn't an explosion like we see on Earth with sound and fury. There was no sound, no fire, no debris. Instead, it was the rapid expansion of space itself, filled with incredibly hot, dense energy. Imagine space stretching and growing at an unimaginable rate, carrying with it the seeds of galaxies, stars, and planets. It was the rapid expansion of space itself, filled with incredibly hot, dense energy. This energy was so intense that it created the very fabric of our universe, weaving together the threads of matter and energy that would eventually form everything we see around us. As the universe expanded, it cooled, and this energy transformed into the first particles and forces that govern our universe today. These particles combined to form atoms, which eventually clumped together to form stars and galaxies. The cooling process was like a cosmic dance, with particles moving and interacting in a delicate balance. The cosmic microwave background is a remnant of that early energy, stretched out over billions of years. It's a whisper from the past, a faint echo of the fiery birth of our universe. By studying this ancient light, scientists can learn about the conditions of the early universe and how it has evolved over time. The CMB is like a time machine, allowing us to peer back to the very beginning and understand the origins of everything we know. So what exactly is the cosmic microwave background? It's a fascinating concept that has intrigued scientists for decades. Imagine a faint glow coming from every direction in space. This glow is not something you can see with your naked eye, but it permeates the entire universe. You can't see it with your eyes, but it's there. It's a remnant from the early universe, a snapshot of the cosmos when it was just 380,000 years old. This glow is made of microwaves, which are like the waves your microwave oven uses to heat food. These microwaves are incredibly faint, but they carry a wealth of information about the early universe. This faint microwave signal is the cosmic microwave background, often shortened to CMB. It's a crucial piece of evidence for the Big Bang theory, providing a glimpse into the universe's infancy. The CMB was discovered by accident in 1964 by two scientists named Arno Penzias and Robert Wilson. They were working at the Bell Telephone Laboratories in New Jersey. They were using a giant antenna to study radio waves from space when they picked up a mysterious signal. This signal was unlike anything they had encountered before. At first, they thought it was interference from pigeons nesting in the antenna. They even went as far as to clean out the nests, hoping to get rid of the noise. But after cleaning out the pigeon nests, the signal remained. This persistent signal puzzled them, leading them to investigate further. They soon realized they had stumbled upon something much bigger, the echo of the Big Bang itself. This discovery was monumental, providing concrete evidence of the universe's explosive beginning and offering a window into its earliest moments. The discovery of the CMB was a huge deal for scientists. It was the first direct evidence we had of the Big Bang. Since then, we've sent several space missions to study the CMB in more detail. One of the most important was the Cosmic Background Explorer, or COBE, launched in 1989. COBE created the first detailed map of the CMB, showing tiny variations in its temperature. These variations, though small, were incredibly important. They represented the seeds of the first galaxies and stars that would eventually form. After COBE came the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck spacecraft. which provided even sharper images of the CMB and taught us even more about the early universe. Section 4. Secrets from the Afterglow. In this section we delve into the mysteries that the universe has left behind, long after the initial burst of the Big Bang. These secrets are hidden in the faint glow that permeates the cosmos, known as the cosmic microwave background, or CMB. By studying the cosmic microwave background, we've learned a lot about the universe. This faint radiation, which fills the entire sky, is a snapshot of the infant universe, taken just 380,000 years after the Big Bang. It's like a baby picture of the cosmos, providing us with invaluable information about its early stages. For example, we know that the universe is about 13.8 billion years old. That's incredibly old. This age is determined by measuring the tiny fluctuations in the CMB, which tell us how the universe has expanded over time. These fluctuations are like cosmic fingerprints, unique in telling a story of their own. We also know what the universe is made of, with surprising results. The CMB has revealed that only about 5% of the universe is made up of ordinary matter, the stuff that makes up stars, planets, and everything we see around us. The rest is composed of dark matter and dark energy, which are still largely mysterious to us. It turns out that most of the universe isn't made of the stuff we see every day, like atoms and stars. Instead, dark matter makes up about 27% of the universe. It's invisible and doesn't emit light or energy, but we know it's there because of its gravitational effects on visible matter. And then there's dark energy, which makes up a staggering 68% of the universe. This mysterious force is driving the accelerated expansion of the universe, pushing galaxies apart at an ever-increasing rate. Understanding dark energy is one of the biggest challenges in modern cosmology. The CMB also supports a theory called inflation, which says that the universe expanded incredibly fast, like a balloon inflating in a fraction of a second just after the Big Bang. This rapid expansion smoothed out any irregularities, making the universe appear uniform on large scales. Imagine blowing up a balloon in an instant. That's what inflation did to the universe. This theory helps explain why the CMB is so uniform, with only tiny fluctuations that give us clues about the early universe's conditions. This rapid expansion helps explain why the universe looks so uniform on very large scales. The secrets from the afterglow of the Big Bang continue to intrigue and challenge us, pushing the boundaries of our understanding and opening new doors to the mysteries of the cosmos. Section 5. Mysteries in the microwave sky. While the CMB has answered many questions, it has also raised new ones. Some of the features we see in the CMB are difficult to explain. For example, there's a strange cold spot that's much cooler than the surrounding areas. What caused this? We don't know for sure. Some scientists believe these anomalies might be hints of something truly mind-boggling, other universes. This idea, called the multiverse theory, suggests that our universe might be just one of many, like bubbles in a giant cosmic foam. It's a wild idea, and we need more evidence to know for sure. Section 6. The Big Bang in our culture. The cosmic microwave background may seem like a complex scientific concept, but it has actually made its way into popular culture. Remember the static noise you sometimes see on an old TV screen when there's no signal? About 1% of that static is actually caused by the CMB. The Big Bang and the CMB have also been featured in movies, TV shows, and books. These stories often use the vastness and mystery of the universe to explore themes of creation, existence, and our place in the cosmos. Section 7. Keep looking up. The cosmic microwave background is a remarkable discovery. It's a window into the universe's earliest moments, allowing us to study events that happened billions of years ago. It tells us a story of a universe born in fire and fury, evolving and expanding over eons to create the cosmos we see today. While the CMB has answered many questions, it has also opened up new mysteries. What secrets do the anomalies in the CMB hold? What will future observations reveal about the universe's birth and evolution? The quest to understand our universe is far from over, so keep looking up at the stars, asking questions, and exploring the wonders of the cosmos.